So related rates are kind of my, almost, they're probably my favorite thing. I really like volumes of revolution and stuff like that too when we get to the end in chapter 8, but it's either this or the volumes of revolution, cross-section sort of stuff, 3D figure stuff that we'll do. So related rates can be very, very, very simple or very, very, very complicated. So, for example, if you have a tank that has a hole in it and water is leaking out of it, then you can figure out, how long it's going to take for the water to leak out. Well, that's a very simple related rate. You might also be adding water to the tank, which will change things even more. So, so you don't necessarily have to write all these words here, and you definitely don't on the next problem. But if you have a tank that is shaped like a cone, this cone is going to have, I'm going to write, it has a radius of r, a height of h. What is the volume formula for a cone? I'm hearing it over here, Addison. Almost. Need one more thing. Times height. A cylinder is going to be pi r squared times height. Yep. So cylinder would just be pi r squared, which is the area of the base, right? Your base is a circle, times your height. Because for any figure that we have that is a, what would you call that? Like a cylinder or a triangular prism. Any prism or cylinder, it's just the area of the base times your height. A cone is 1/3 of a cylinder that has the same radius and height. So if you have a cone like this and it is being drained, we want to talk about the rate at which the volume is changing. So if you have a cone like this, whenever you drain water, like here would be, like let's say we had water that was, to this level. So the water, more or less, we're going to kind of ignore like the fact that gravity sort of, if there's more weight of the water, it's going to come out a little faster at first and then less fast at the end. We have to kind of ignore that for our purposes here. Or we could say it's being pumped out so that doesn't matter. But yeah, friction's always negligible. We are not smart enough to figure out what to do with friction at this point. We don't, yeah. So if I have water in the cup right here, and I'm thinking about the height of this water, is the height of that water going to change at a constant rate? So, volume is going to, like, let's say we're pumping the water out, right? So it's not, the weight of the water doesn't matter. You're pumping the water out. The volume would change at a constant rate in that case. So the volume would change at a constant rate as you pump the water out. But what about the height? Because is there more water in this part of the cone or way down here in this part of the cone? Like those top layers have more water, right? So whenever you're draining it, the height is going to change slowly at first. But whenever you get down to that little tiny bottom part, it's going to be changing a lot more quickly because there's not as much water there, right? So what we'll be talking about is we'll be talking about taking derivatives of this function. So dv dt, okay, I I'm taking a derivative with respect to a third variable. That variable is time, because the water is being pumped out over time. It's not in this function. So this is dv dt. So basically, remember when we did implicit differentiation with dy's and dx's, and every time you took the derivative of a y, you had to put dy dx with it? This is similar, but we're going to be taking the derivative with respect to t, which is not even a variable in the equation to begin with. So basically it means every time you take a derivative of something, you have to put a d whatever dt, dr dt, dh dt, dv dt. So every time, not just with the y's for this. So like if I took the derivative here, I'm just going to leave the, I'll switch back to 3. All right, so I'm going to just leave the 1/3 and the pi out front because those are just coefficients. But then I would have r squared times the derivative of h, which would be dh dt, plus h times the derivative of r squared, which would be 2r dr dt. Now, this is not an actual problem. This is kind of like the setup, and I'm wanting you to notice what some things stand for, because they didn't ask us to find any specific thing, right? So, in this equation right here, this dv dt is the rate of change of volume with respect to time. And so that volume, it might be measured in cubic feet. Time can be measured in minutes, seconds, hours, something like that. It'll be specific to the problem. The dh dt here would be the rate of change of volume. Oh, no, sorry, not volume. Sorry, I was copying everything there. You copy most everything, but the rate of change of, not volume, but height, with respect to time. And then the last one that we would care about here would be your dr dt, which is the rate of change of the radius with respect to time. So where we're going with this is that we will be looking at different rates of change. And so this next slide, don't try to write any of this down. I just want to give you an idea of where this can go. Okay? So like this would be like at the very end of related rates. Maybe we could do this problem. This is probably a little harder than what I would give you, but all right, so let's say that we have a swimming pool shaped like the one below, has a leak that is causing the height of the water to drop 9 inches per day. Once the leak is discovered, the lifeguard, many of which of you are in here today, starts filling the pool with a water hose that adds 6 gallons per minute to the pool. How long will it take for the pool to either drain or overflow? Assume that a heavy rain just filled the pool to full capacity. Assume it does not rain anymore until the pool is drained or overflowed. So, no, you don't have to write anything here. I just want to give you an idea of what you're talking about. So, right, so really the question here, I know the water level's dropping at 9 inches per day before Thomas adds the water hose to start filling up the pool. That might even be right. Are you a lifeguard? Okay. So Thomas decides to start filling up the pool. So if he knows that the water hose puts out 6 gallons per minute, but that's way different than 9 inches dropping per day. He doesn't really know how that compares, right? So, if 9 inches per day is more than 6 gallons, eventually it's going to still drain out. The water hose is just not pumping enough water in to make up for the water loss. But if the water hose is actually adding more water than the pool is losing, then eventually it would overflow in that case. So you would have to figure this out. This would be a really complicated problem. It's not too bad until the pool starts to get down to this section, because up here you're just dealing with like a rectangular prism, but the deep end is going to cause you some issues whenever you're trying to figure out if it's going to overflow or not here. But this is like the direction that you could go with this, which is really important. I'm sure that they train all rec center lifeguards in this so that you know what to do if this happens. So yeah. So anyway, this is just like an idea that I felt like we could probably relate to and understand. Certainly it's probably not going to be something that a high school kid that's lifeguarding is going to do, but think about more volatile situations. Think about a tank that might be holding like important chemical or oil or something like that that's way more important. Consider possibly that you might not be able to fix the leak, or you have all kinds of different things that you might need to know about. So all of this can kind of work together. Anyway, I gave you these two problems to give you an idea of the direction we're going, because today we are going to do nothing but naked problems that have nothing to do with actual situations. Okay, we're starting here just so you can get a feel for the mathematics, for the process of it. Okay, so these are just basic problems. Tomorrow we will get into actually applying this into situations. So we have this equation, so you can copy that down, and we want to find dy dt when x equals 1 and dx dt equals 2 in this particular case. So those are your key pieces to copy down. I'll give you a second. So all the rest of the time that we've been doing these problems, we've been taking the derivative with respect to x. Even when we were doing our implicit differentiation, it was still dy dx. So we were taking derivative with respect to x. But they're asking us to find dy dt, which means with respect to t. So since there are no t's, that means every time we take a derivative of any variable, we have to put d, whatever that variable is, over dt with it. So whenever we have y equals x squared plus 3, if we take the derivative of y, it is going to be just 1, but with it, you have to put a dy dt. When we take the derivative of x squared, we get 2x, but with it, we must put dx dt. And then the derivative of 3 is 0, so you don't have to put anything there. Okay? So, with these problems, you're going to take the derivative, and basically you're just going to plug in the rest of the information that you're given. So they tell us whenever x equals 1, dx dt equals 2. So we can plug in 1 for our x, and our dx dt at that point is going to be 2. So we replace the dx dt with 2. And so our dy dt equals 4 when x equals 1. Yes? You do not have to show that. When you get your answer at the end, I just put like this when x equals 1 at the end to let me know that's the time I was looking at there. But there's not like a standard, like with our dy dx, there was where we did that line and put the xy equals, but there's not really a standard way of doing that here because you're going to be plugging in for different variables in a lot of different cases. So in general, just go ahead and plug it in, but when you get your answer, give that qualifier at the end with your answer. Good question. All right, let's do another one. All right, so this time we have x squared plus y squared equals 16. What's that the equation of? What's it look like? Circle with a radius of 4. Okay. We're supposed to find dx dt when x is 4 and dy dt is 3. Alright, so derivative of x squared is just 2x, but we must put with it dx over dt plus 2y dy dt equals 0. And so once you have taken your derivative, you're going to plug in the information that's given. So x equals 4 and dy dt is 3, and it tells us to find dx dt, so you're not replacing dx dt because that's what you're trying to find. But y, I don't have anything to plug in for y. I can't just leave it. I just plugged in the 4 went right here, and the 3 went right here. But I need the y, so that's why I left that space right there. It is not 16. I think I might have heard somebody say what it was. It's 0. How do we know it's 0? Alright, so this original equation has to be true. So if I plug 4 into the original, so 4 squared plus y squared equals 16, then I can solve that equation for y to find the y coordinate whenever my x coordinate is given. Ethan, what you doing on your computer there?
Cheating.
Okay. Okay. Make sure you're with me. All right. So y squared is 0. So y is 0. So we're going to plug in 0 right here. So we end up with 8 dx dt. This is just 0. This equals 0. So the dx dt would also have to equal 0. I do not like it when answers like that end up being 0. We should. We should say when x equals 4. Because this would be different if we were looking at like when x equals 3. Right? Because we'd have different numbers that we plug in. Okay, let's try another more difficult one. This is probably going to be the last one we get in. Alright, now this is more or less, it's very similar to what we were doing for implicit differentiation. But we're taking the derivative with respect to t instead of with respect to x. So everything needs whatever dt with it. Oh, you kind of do it backwards for me. You can do it your way you're doing. But 2x times the derivative of y, which would be dy dt, plus y times the derivative of x, which would be 2 dx dt, plus 2y dy dt equals derivative of 8x is 8 dx dt. Alright, they give us y equals 1. So, I mean, you could simplify. I'm just going to start plugging in. So we can plug in a 1 here for our y. They tell us dx dt is 5. So dx dt, which actually shows up here and here, we can plug in our 5. Our y, should put a red box around that, it's also 1. We are finding dy dt, so we don't want to replace dy dt. But Thomas is right. What about this x right here? And we cannot just cut it out. We got to figure out what it's supposed to be. So, where do I go to figure out what that x is supposed to be? Original problem. So 2x, y I know is 1 at this point. So 2x times 1 plus 1 squared equals 8x. So I've got 2x plus 1 equals 8x. I can divide. Ooh, don't do that. Oh, gracious me. What is wrong with me?
I would have done that.
Subtract 2x. 1 equals 6x. And we get 1/6 for our x. Ugh. At least it is only one spot. So we can plug all of our information in now. We got 2, 1/6, dy dx. We don't know that we're going to keep here. Plus y is 1 times 2 times dx dt, which is 5, plus 2 times 1. dy dt, I don't know. I've got to leave it. Equals 8 times dx dt, which is 5. 2 times 1/6 will give us 2/6, which is 1/3 dy dx plus 10 plus 2 dy dx. Oh, it should be, sorry, it should be t's. Alright, I can put both these dy dt's together. I gotta do 2 plus 1/3, which would be 6/3 plus 1/3, which give me 7/3. 7/3 dy dt. I can subtract that 10, so that would equal 30. And then I need to divide by 7/3, or I could just multiply by 3/7. That's a little bit quicker. That's the same as dividing by 7/3. So dy dt would be 90 over 7. Let's just leave it like that. It's not going to go evenly or be an easy decimal to deal with. Okay, so we didn't get to every example, but I think we should have the idea. This example was, we were going to do like an actual application. You're not going to have applications on your homework. So, on page 194, I want you to do 1 through 8, but only do part A on each one, because it asks you to plug in different numbers, which means you can have to do the problem again a few times, and I just need you to do it one time each. So, just part A on all of those pieces.